from. Just to recap, we have been talking about ideal diode model, which means that in case we have ideal diode model. So this is anode, we denote it by VA, and this is cathode voltage, we denote it by VK. So anode voltage has to be VK cathode voltage for it to consider as a piece of wire. Now, if anode voltage is less than cathode voltage, if anode voltage is less than cathode voltage, then it is simply an open circuit. As simple as that. But in reality, the way diode is constructed, diode is a semiconductor device. Therefore, as you can see, it is constructed with semiconductor materials. We have P-type semiconductor material and N-type semiconductor material. So these P-type semiconductor material and N-type semiconductor materials are actually joined together to form a p-n junction. So this is called p-n junction. P-n junction. Now, if you apply voltage between anode terminal and cathode terminal, VF, so this is negative, this is positive. If we apply voltage, then so there is a depletion region here. This depletion region becomes very, very narrow, and most of the current flows from P-type to N-type. So most of the current flows from P-type to N-type, and that's why you see that this arrow is larger. And then, because of the property, because of the semiconductor materials, some of the N-type material, they are in the other side, and some P-type material, they are here. They are arranged nicely. Because of this construction, a small portion, it's called reverse saturation current, a small portion of the current will be flowing in the opposite direction. This is very, very small. Very small. This is the key word here. Very small reverse saturation current. It's called reverse saturation current. And you will see in a moment. It's called reverse saturation current generated with IS. It's very, very small compared to ID. Yes.
So it's like microamps, not small.
Yes, even less than nanoamps. They're very small. So that is the physical construction. Oh, you still do not do that.
Yeah.
I'm very sorry, Alex.
Yeah, no, it's fine. I keep talking to them about it, and they just say they fixed it.
So, because of the physical construction, we see some reverse saturation current will be flowing. Now, this is basically the practical version of the diode. Now, we will not consider ideal version of diode anymore. Now we know the construction mechanism of the diode. We know the construction mechanism of the diode. Therefore, we will not consider an ideal version of diode anymore. Because of this depletion region, you will see the voltage difference, the voltage drop in the p-n junction is, we call it VD. It is going to be standard for standard diode in general. There are many different versions of diode manufactured by many companies, different companies. So standard voltage drop, we will see it is going to be 0.7. Now, because of this depletion region, so standard voltage drop that we are going to consider, it is going to be 0.7 volt. Now, guys, Schottky diode, there are Schottky diodes, there are many other diodes manufactured by different companies, and you also you did use a Schottky diode, and for your laboratory assignment, you did measure the turn-on voltage, right? Using multimeter, right? You remember, guys? So there is an option for turn-on voltage. there is a diode symbol, right? There is a diode symbol in multimeter, and between anode terminal and cathode terminal, you measure the voltage. You measure the voltage, and that voltage you saw it is 0.2 volt. Okay. So for other diode, you guys used Schottky diode, so it is 0.2 volt. For other diode, it could be 0.8 volt, 0.7 volt, 0.3 volt, 0.4 volt. So it depends on the manufacturer. Okay. Standard terminal voltage for diode, we are going to consider is 0.7. If I do not mention anything in the exam, okay? If I do not mention anything, I say that it is practical diode, it is not ideal diode. So if I do not mention anything, you consider practical diode, and you consider the voltage drop for the diode is 0.7. Is that clear, guys? If I do not mention anything, then you consider that it is a practical diode, and the voltage drop across diode is going to be 0.7. That's it. So make sure you just keep this in mind, that the diode voltage drop is going to be 0.7. And based on that, I did kind of reverse the explanation here, in case you have negative terminal connected to anode and positive terminal connected to cathode. In that case, you see that reverse saturation current is more and the forward current is less. So in that case, diode is going to be simply, ideally it is open circuit, but practically you will see some saturation current will flow in the other direction, and almost zero current will flow in this in the forward direction from P type to N type. Okay, so under these practical circumstances, scientist Schottky, actually this is Schottky's model. Schottky equation. It's called Schottky equation. Scientist Schottky came up with the relationship, mathematical relationship between the diode current and the voltage across it. So we have a diode model, practical diode model. So we have a practical diode model now. And the current flowing through this practical diode, we denote it with ID, both DC plus AC component. And the voltage difference between the anode terminal and cathode terminal, we denote it with VD. So scientist Schottky came up with a mathematical relationship between the diode current flowing through the diode, and the voltage across the diode. Now, if you plot, okay. By the way, we know what is this. It is called reverse saturation current, and we know VD, we know ID, and this VD is the only term that you do not know. So at room temperature, this VD is called the thermal voltage. So this is called the thermal voltage. At room temperature, thermal voltage for the diode is, this VD is 0.025 volt. In other words, 25 millivolt. So in other words, 0.25 millivolt. You can just bring this number in your formula sheet as well. Okay. So this thermal voltage for a diode, when he came up with this equation, he experimentally determined that this VT is 25 millivolt, in other words 0.025 millivolt. Now if you plot, if you vary VD, if x-axis is VD and y-axis is the current in milliampere, then you will see the characteristics, IV characteristics. It's called IV characteristics. We call this IV characteristics of diode. IV characteristics of diode. Now, you see that when the voltage VD is 0, then the current is 0, and you increase VD all the way. Okay, I did use a different diode model, but practically you will see at about 0.7 volt, at about 0.7 volt, that's the standard number we are using. At about 0.7 volt, you see that the diode current is drastically increasing. Okay, diode current is drastically increasing. So you can think of this as a piece of wire at that moment. But this voltage, people call this voltage as knee voltage. So the voltage at which the diode current is exponentially increasing. And because the voltage and current relationship is non-linear, that's why the diode is called non-linear device. Because the voltage and current relationship is non-linear, it is not linear like Ohm's law resistance. Okay, that's why diode is called non-linear device. Now look at the other side. The other side of this characteristics is, you see, so when VD is negative, you see some current is flowing. So here this current is I sub, this current is I sub S. But at some point, if the reverse bias voltage is, let's say, very, very large, at some point you will see that the current will flow in the opposite direction, but it's negative exponential. Okay? And there is another type of diode called Zener diode. It's called Zener diode. This type of diode operates in reverse breakdown region. It is called reverse region, but because of these characteristics, that after certain voltage, it is called reverse breakdown region. And only this type of diode operates in reverse breakdown region. And we will see how this Zener diode is used for voltage regulation. So you guys use 5-volt regulator, right? You guys heard about regular voltage regulator, you guys heard about this term by now. So in most cases, you will see those voltage regulators, 5-volt voltage regulators, 12-volt voltage regulators. Those voltage regulators are actually built with Zener diode. So we'll talk about that. Now, let's go through one example where we utilize this equation. So in this example, a silicon diode is said to be a 1 milliampere device. Silicon diode is said to be, guys, I need your help for calculation. So if you have calculators, some of you please give me open up the calculator. So a silicon diode said to be a 1 millimeter device displays a forward voltage of 0.7. Forward voltage VD equals 0.7. Okay. And so at 0.7 volt, you see that the forward current is 1 milliampere. So ID is 1 milliampere. Evaluate the junction scaling constant. In other words, reverse saturation current. Junction scaling constant, people call it junction scaling constant, I sub S, and there is a name for it. So author did not put this name. It's called reverse saturation current. Okay, so this is the name. So evaluate the junction scaling constant IS given given these parameters. And what scaling constants would apply for 1 ampere diode of the same manufacturer that conducts 1 ampere at 0.7 solution. Look, 1 ampere, before it was 1 milliampere. Same manufacturer, but this time 1 ampere current has to be has to pass 1 ampere. Guys, there is a difference between 1 milliampere, 1 ampere. Before the label is 1 milliampere device, 1 milliampere device diode. Now, same manufacturer, but a 1 ampere diode has to be designed. Okay, so this is what the problem is. So we will need to design this scaling constant for 1 ampere diode that will operate at 0.7 volt solution. First part. First part, we are going to use Shockley equation. Of diode model. So it is going to be ID equals I sub S. What was the equation, guys? E to the
VD over VT.
VD over VT minus 1, right? VD over VT minus 1. Now, here, guys, you will see when you have VD equals 0.7, in that case, this term is much larger than 1. So therefore, you can actually approximate this equation with I sub S e to the VD over VT. So now, I sub S is going to be ID times e to the negative VD over VT. VT is the thermal voltage. Which is 0.025.
How do you know 0.025 volt equivalent voltage?
For thermal voltage, it has been experimentally determined, and there is a formula for VT. So this VT is VT equals K over N Q. Okay, K is the Boltzmann constant, and N is actually between 1 and 2, and Q is the amount of charge. So using all these constants, the scientists came up with this voltage, 0.025. So we do not, this is very low level, so we are not going to use that equation here. We are going to directly use 0.025. So if you use Boltzmann constant at, what is the standard Kelvin temperature at chemistry? 300 Kelvin, right? So the standard temperature, at standard temperature it's 300, standard temperature is 300 Kelvin. At 300 Kelvin, there is a Boltzmann constant, there is a number for Boltzmann constant. So if you divide that Boltzmann constant with the charge, the value of charge of an electron, then you will get this voltage. So we will be using this thermal voltage directly in this equation. So this ID is 1 milliampere, which is 10 to the negative 3, and e to the negative 0.7 over 0.025. Guys, could you please give me your result? 10 to the negative 3 need to be, and this is going to be ampere. Unit is going to be ampere. So I put it in volt. Exactly. Calculation of common calculator. Now keep this number. Somebody has this number.
I got something wrong with that thing.
Okay. So IS equals, I'm using MATLAB. What was that? 1 e to the negative 3, 10 to the negative 3 times exponential of negative 0.7 divided by 0.025. Yeah.
Oh, yeah, okay, well, I thought
Okay, so it is 6.91. It is 6.91 times 10 to the negative 16 ampere. So this is your scaling constant, which is basically the final answer. Now the second part. Second part, you have 1 ampere diode. Okay, so you have one manufacturer actually manufactures 1 ampere diode, 1 milliampere diode. So to design an 1 ampere diode, so don't you think that you would have a diode here, another diode right here, and so on, another diode. So this is 1 milliampere, this is 1 milliampere. Now, if you connect all of these, so this is your piece of A, and if you connect all of these, this is piece of A. Piece of K. So piece of A minus piece of K is going to be still 0.74. Okay, because we connected these diodes in parallel. Now to get 1 ampere current here, to get 1 ampere overall current here, so we are designing 1 ampere current. Okay, to get 1 ampere current, how many diodes need to be connected in parallel? One small diode we have, it gives the rating is 1 milliampere. Now to get 1 ampere current, how many diodes need to be connected?
Just did 1,000.
1,000. So you need 1,000. 1 milliampere diode needs to be connected in parallel. Okay, so So now the scaling constant is going to be I sub s is going to be I sub d and e to the negative Vd over Vt. Now this I sub d now is 1 mpd. So it is going to be 1 times e to the negative 0.7 over 0.025. How much is it, guys?
It's 6.91 times 10 to the minus 15.
Exactly. So before it was negative 10 to the negative 3. Now it is multiplied by 1000, right? So it is going to be same 6.91 times 10 to the negative 30 mpd. So this is going to be here. As you can see, this is very, very small number, which makes sense with the theory that I went through, that a scaling constant or reverse saturation current has to be very, very small. Okay. So this is one example that I went through the complete solution. Let's move on to more complicated circuit. Okay. So just to reiterate, we are now dealing with practical diode. So therefore, we'll have we'll build circuit using practical diode. We start building a circuit using practical diode. So if we have a voltage drop here, voltage source here, we denote it with VDD, and this is a DC voltage source. So this is simply a DC voltage source. DC voltage. Okay. We connected one resistor in series with this DC source, and then we have a diode. Now, question here is, what is ID? ID equals what? And what is the voltage across this diode? Now, we are going to solve this circuit. Again, solution of this circuit means that we want to find the voltage flowing through each component. We want to find the voltage across each component. We want to find the current flowing through each component of this circuit. So we have a voltage VDD. We want to find what is the current flowing through this R, which is the same current flowing through this diode, because they are connected in series. And we want to find what is the voltage. Now, this circuit can be solved, can be analyzed. This circuit can be analyzed using two different diode models. We can use this Shockley equation. We can use this Shockley equation or exponential model, or we can actually just straight write down the constant voltage drop across diode. Okay? We can write down the constant voltage drop across diode, which is V is going to be 0.7. So we can use this constant voltage drop model where we know the voltage across this diode, or we can use the Shockley's exponential model for the diode as shown here. Now, if you, I'm not going to write it down because I wrote the steps here. If you apply KVL, so I'm analyzing this circuit. If we apply KVL, Kirchhoff's voltage law, so this voltage has to be equal to the sum of voltage drop across R and the voltage here. So suppose that we are using Shockley's equation, exponential model. In that case, we have VDD equals IDR, voltage drop across this resistance is going to be the current flowing through this resistance ID times R plus Vt. Now, if we substitute the Shockley's equation into this KVL, so we come up with this nonlinear equation. Now, if we use just going to make you understand here. So we have Shockley's equation ID, which is Is into the negative into the Vt, Vd over Vt, and you have VDD equals ISR into the Vt over Vt plus. So we have two unknowns, Vd and Id, two equations. We have two equations, we have two unknowns. Therefore, we should be able to solve for Vd and Id, right? Right? So here we have Id equals Is equals Is into the Vd Vd over Vt, and then you have VDD equals Is R into the Vd over Vt plus Vt. So I have two different colors here. So this is equation number 1. This is equation number 2. Guys, do you see? I have two unknowns and two equations. And these two equations are nonlinear equations. Now, you guys, this latest version of calculator, like TI, the graphical calculator that these days have, TI, the latest model. Do you know what is the latest model? CX. You know, I bought one of that for my daughter. So you can directly enter this nonlinear equation into the calculator, and calculator will give you two values. So here, all the parameters that you see in blue, these parameter values are known. So Vt you know already, 0.025. You know what is Is. Is is normally given in the data sheet, okay? And VDD is the voltage source coming from the DC voltage that is given, and resistance R is given. So you have these two equations, and you have two unknowns. You can directly find. Solve these two nonlinear equations using calculator. Or if you don't want to use calculator, there are some other methods called Newton-Raphson method. You can use these nonlinear equations using Newton-Raphson method, and you will see you will be able to find the values of I and P. Right? Okay. In other words, if you don't want to use this exponential model, you can use the constant voltage drop model. Constant voltage drop model, the way it works is the following. You start with KVL. start with KVL using the second constant voltage drop model. You start with KVL. VDD equals ID R plus VD. Substitute ID equals 0. So substitute ID equals 0. So your VD is going to be VDD. So it is going to be right here. It is this point. It is this point. Okay? And to find this point, now what you do, you substitute, you go through VDD equals ID R plus VD. Now you substitute VD equals 0. So in that case, ID is going to be VDD over R. Okay? So this value is going to be right here. This is point A. Now you draw a line like this, and this line is called load line. This line is called load line. This line is called load line. Now what you do, you can draw the diode characteristic line. This is using Shockley equation. IS into the VD over VD. You can draw this Shockley equation, and the intersection of this load line and this diode characteristic curve is called the operating point. And this is your VD and this is your ID. And you will see that this VD is going to be approximately 0.7 volt. This VD is going to be approximately 0.7 volt, and ID whatever value you get. So you will have to solve this straight line equation, and you will have to solve VD and ID from this straight line equation and this diode characteristic curve. So this intersection point is called Q point. This intersection point is called Q point or operating point. And this Q point is nothing but the voltage across the diode, which is going to be approximately 0.7 volt, and current flowing through the diode. That's called the Q point. Okay? So I have one example. Okay, I'm going to stop for a minute here so that So that next example that I have, I typed the solution of that example so that I save some time. I'm just going to make you understand the solution, but that's how it works. So we can solve current and voltage of a circuit that consists of a diode using two different methods, two different models. One is using exponential model, the other one is using constant voltage drop model. So constant voltage drop model, we are going to think of this diode as 0.7 volt drop. That's all. That's all. So in most cases, we'll be using that constant voltage drop model for simplicity. But actually, to be more accurate, we can use computer and then solve the Shockley equation version of the circuit. Alright, so let's go through this numerical example. Okay. So I have provided the solution. Those who downloaded the latest version of my site, you guys see the solution, right? In your iPad. Okay. So I'm not going to type anything here. Write anything here. Solution is done. Determine ID and VD of the previous circuit using VDD equals 5 volt, R equals 1 kilo ohm. So I just came up with these numbers. Okay. I just came up with these numbers. You just need to substitute these numbers in the previous circuit. So this is the circuit. VDD equals 5 volt, and then we have a resistor here R, which is 1 kilo ohm, and then we have a diode. We determine VDD. We determine VD and ID. ID is going to be the current flowing through this diode, and what is VD? VD is going to be 0.7 volt if we use constant voltage drop model, because we know that for a standard diode, practical diode has a voltage drop of 0.7 volt. So we are going to use this Shockley's model. Diode model. So if we use this Shockley's diode model, ID equals IS into the VD over VT. So which is approximately IS into the VD over VT. And apply KVL. KVL VDD equals IDR plus VD. So therefore ID is going to be 5 minus VD over 1000. Now, because we are using Shockley's equation, so you just substitute this ID right here, expression of ID right here. So you get the expression of ID in Shockley's equation, and reverse saturation current is 10 to the negative 12 ampere, and then we have e to the VD over VT is 0.025. Now, this is equation number 1. This is equation number 1. This is equation number 2. If you solve these two equations, if you solve these two equations numerically using Newton-Raphson, you will see VD equals 0.74 volt and ID equals 4.26 milliampere. So, as you can see, it is approximately 0.7 volt if we use Shockley's equation. If you do not use Shockley's equation, so there is another way. So you just assume for constant voltage drop model, you just assume that the voltage drop across diode is going to be 0.7. So you know, you already know what is voltage drop. Now all what you need to know is what is ID. Now, ID, you just apply KVL. KVL VDD equals IDR plus 0.7 volt. So you solve for ID, and ID is going to be 4.3 milliampere. So which is approximately 4.26 here, here 4.3. So they are approximately. Okay. So you guys can use constant voltage drop model, or you guys can use the Shockley's equation. Shockley's equation you need to solve through nonlinear equations numerically, or as I said that you can use a calculator. I don't mind if you know you can bring the latest version of TI calculator or sophisticated scientific calculator, and if you can solve, this is not a math class, as long as I know that you are determining the current and voltage properly, I'm fine. Okay, there is no restriction in the calculator. All right. Now we are coming to another model of diode, another version of the diode, another type of diode. So it is called Zener diode. Zener diode. This diode operates in reverse breakdown region under high reverse voltage, which means that we saw the diode characteristics curve. We saw the diode characteristics look like this. Okay, so this is ID and this is VD. Okay, and you see the some small character. So this is almost vertical, but it's not exactly vertical, but it is going to be almost vertical, and that's how it works. That's how Zener diode works for regulating voltage. So in case you have the input voltage, you can vary input voltage, that the output voltage is going to vary by a small amount, so almost constant. You will see almost constant, and this voltage is called VBR. This voltage is called VBR, which is negative VD. Okay, which is negative VD. So this voltage is basically large. Magnitude is going to be large. VBR magnitude very large. So this reverse breakdown region is very large. Reverse breakdown voltage is going to be very large. Magnitude is very large. If you just take out the negative sign, magnitude is going to be very large. Now I explained here. There are two breakdown mechanisms here. The way this Zener diode works, there are two different mechanisms. One is Zener effect. So usually 5 to 6 volt. In case you want to develop a voltage regulator in the range of 5 to 10 volt. But there is another effect called avalanche effect, where dominant that effect dominant at higher voltages, which means that the breakdown voltage is going to be greater than 10 volt. And peak inverse voltage, in the data sheet you will see this term as PIV. People call it PIV, peak inverse voltage. Peak inverse voltage is the maximum reverse voltage the diode can put without breakdown. So after that voltage, after this voltage, so PIV is going to be right here. After this voltage, diode operates in reverse breakdown. So after PIV, right after PIV, up to PIV, diode operates in reverse region, but right after PIV, it operates in reverse breakdown region. Okay? So then PIV is important. PIV, the definition of PIV is maximum reverse bias voltage, after which diode operates in reverse breakdown region. So here wording is a little bit different, but meaning is the same thing. So maximum reverse voltage a diode can withstand without breakdown. So what I'm saying that up to PIV, it operates in a reverse bias region. A diode operates in reverse bias region. Right after PIV, it goes to the reverse breakdown region. And that reverse breakdown region where this Zener diode operates. Zener diode operates in reverse breakdown region. So you may want to write it down in short. That operates in reverse operates in reverse breakdown region. And I have one example typed solution in this model. So I will allow you to understand that. And Zener diode, actually in PSpice model, in PSpice diode model, you will see Zener diode, this sort of symbol you will see in PSpice, ORCAD PSpice as well. PSpice model you have, Zener diode symbol is like this. Okay? So you should be able to easily distinguish what is Zener diode, what is the normal diode. And Zener diode because the symbol is the other way around. You see guys? So negative here, positive here, and it operates in reverse breakdown region. So VC is going to be V underscore C, subscript C is going to be the voltage. Okay? So equivalent circuit of this Zener diode is as follows. So you have this VC, and you can think of this diode, Zener diode, has a voltage source of VZO under open circuit condition, and there is a small internal resistance. There is a small internal resistance. So therefore, around the operating point, around the Q point or operating point. So I just went over what is Q point or operating point. So around this operating point, if this diode behavior, this Zener diode behavior is linear. So VC is going to be VCO plus whatever current flowing through this Zener diode IC plus RC. So this is a linear equation. And again, the key point here is that around the operating point that we just went over. So let's see how to utilize this internal resistance. This internal resistance is also present in diode, normal diode as well. We can model this resistance, even though we don't see, but we can model this resistance around operating. So let's go through those circuit models. Now, before I do that, here I'm not going to read my slide. So this Zener diode mostly applied or mostly used in voltage regulation. So input voltage can vary, but output voltage stays nearly constant. So for voltage regulator to implement voltage regulator circuit or voltage regulator device, you use Zener diode. So Zener voltage VC is specified by the manufacturer. So if you look at the data sheet of Zener diode, manufacturer actually provides this VC, what is VC. And diode must be biased properly with series resistors to limit IC. So you will see in a moment. Now, so based on the equivalent circuit that we have right here, please solve this exercise. So this is scribing, which is part of the list of problems that I'm going to post. Okay, so this is 4.15 and 4.16. These two exercises. Now, let's see how to model this internal resistance. We are going to use a small signal model. Small signal model so we have large signal, mostly DC voltages, and we have small signal. Small signal that is very small, very small, less than 5 millivolts. We are going to deal with signal of less than 5 millivolts. Okay, so if we deal with signal less than 5 millivolts, we call them small signal equivalent circuit. Okay, so if we have a circuit that deals with voltage less than 0.5 millivolt, So those circuits we are going to call small signal circuit, and the diode that operates under this small signal, the diode model that operates with this small signal, we call this small signal diode model. Okay? The diode that operates with this small signal, which is voltage less than 5 millivolt. So those diode models, we call them small signal diode model. So it will be clearer here, right here. Practically, so let me explain a little. Before I come to this slide, let me just draw the standard circuit. Okay, guys, please pay attention, otherwise you will get confused here. So this is the circuit diagram that is not in the slide. So we deal with the voltage source. We deal with the voltage source, and we denote it with VS. VS or V. Okay. VS. V is lowercase, S is uppercase. Okay. See the note the symbol. Now we have a resistor connected in series, and we have a diode connected in series. So this diode voltage, I am not going to denote it with V subscript uppercase. This consists of VD, which is the DC voltage, plus delta V. Delta VD, or you can say V, or you can say delta VD. Okay, so this part is the small signal. So this voltage now consists of this DC component, which is large signal, and this part is the small signal. And this voltage source is going to be consists of two parts. One is VDD, which is the DC part, plus small signal VT that can be varied. Small signal. So this entire circuit now can be divided into two parts. This entire circuit can be divided into this battery voltage, which is VDD, and here you have plus minus VD. This is ground, and the other part of the circuit is as follows. So we have time varying small signal, which is VDD, and this resistance R, and then we have this diode introduce a small voltage that corresponds to, that actually goes through small resistance RD. Small resistance RD. And this small resistance RD, the voltage drop is going to be delta V. Delta VD. Okay? So you now have two different version of circuits. So one is the total circuit where we practically see. Now for analysis purpose, we can actually think of these two different versions. This is the large signal version and this is the small signal version. Small signal, I'm saying that this voltage, V subscript lowercase d, which is a time varying signal, you can think of this as a noise voltage, okay? And this voltage is going to be less than 5 dB. So now let's move on to my previous slide, where I actually omitted this total circuit. So this circuit is divided into 2 parts. This circuit is divided into 2 parts. First part, we call it DC operating voltage. So we find the DC voltage, these are DC voltage, DC component. DC component, DC voltage and DC current. Okay. First, we consider that the small signal is going to be 0. We consider small signal is 0. We start with the DC voltages. So you have DC voltage, battery voltage, and you have current, and then we have DC voltage. DC voltage VD, which is across the diode. Now, total current. Total current we denote it with I sub d, I, lowercase I, uppercase d, as a function of time, is going to be I sub s e to the negative, e to the v sub d over vt, v sub d over vt, and v, lowercase v, uppercase d. Now, you substitute v sub d, t, so this is going to be time varying, with vd plus vd, v lowercase d, so this is a small signal. Okay, so now you substitute that, and make sure this lowercase vd with respect to this vt is going to be very, very small, very, very small compared to 1. So this vt is going to be, less than 5 millivolt. So in that case, you will see there are a bit of derivation. I'm not going to go through the derivation. I'm going to directly write down the total current here. This total current is going to be ID times 1 plus VD over VD. So this VD is going to be the small signal that is coming right here, and ID, if you multiply ID, so you get ID plus ID over VD times this lowercase, this is small signal part, and this entire part can be modeled as a small signal current. So this is basically the small signal current. Small signal current. This is a small signal current, and VD, I said that it has to be less than 5 millivolt, and VT is 25 millivolt. Now this small signal current can be modeled. Small signal current will flow through the small signal resistance RD, this RD, and this RD is basically VT over V sub t. So make sure you know that this VT over V sub t for constant voltage drop, it is going to be 0.025 over 0.7. So for constant voltage drop model, this RD is basically around much is it? It's 26. Could you please quickly put this in the calculator? 0.025 over 0.7.
Zero point 0357.
0 point
0.0357.
357 ohm. Okay. So this is the small signal resistance. You see that this much resistance, about this much resistance is present in a diode. You can think of this internal resistance. Now let's move on to this example. So consider the circuit shown to the right. We do not have time. We do not have. I wanted to go through this example. Requires a bit of time. Anyway, so this example, I'm going to go through this example in our next class. So the quiz syllabus is going to be up to this point. I will give a small numerical problem based on the formula. So the quiz syllabus is going to be up to this point. Slide number 329. Up to slide 329. So you may expect like about 20 minutes quiz. One problem. 20